Matthew, and our experiment is basically the speed at which things dissolve and how we can affect this, right? So the first part, my part, is how heat can change the speed at which things dissolve. So my hypothesis is that the warm water is going to dissolve the sugar cubes. We have sugar cubes in all these cups. You see, this is the control group cup. I have a hot water cup here. I don't know if you can read it, okay. And I have a cold water cup here. And I think that the hot water that I'm going to pour into this cup is going to dissolve the sugar cube fastest, while the cold water is going to dissolve the sugar cube the slowest. My cup for my hot water that's designated as hot water. I have a timer over here, and I have my hot water. To ignore what it says because it doesn't matter, but my hot water isn't here. All the water that I'll be pouring in the cups is a measurement of 1 cup each, just so you know. Okay, so 3, 2, 1. Oh, that spilled a bit, but it's fine, okay? You can see, I think it's starting to dissolve a bit. I will come back when it is fully done, but it's doing it fairly quickly. I think you can see it on camera, at least a little bit. You see it's slowly falling apart? Okay. Actually, it's falling apart really quickly. I don't think I'll have to stop. Okay, so it's mostly fallen apart, but I'm gonna pause and I'll be back when all this powder down here is done. Okay, so there's a little bit left at the bottom. Okay, and stop. They're all done, and we are at 2 minutes and 9 seconds. It's reversed, but it's 2 minutes, 9 seconds, and 0.28 of a second. Okay, so that's the hot water. Make sure to take note of that, and we will be doing the control group next, which is just room temperature tap water with sugar. Hello. So our next group of water is our control group. I was just testing to see which one is the cold and which one is the control, because I have them in the same type of cup. But this is our control group, and I have room temperature tap water here, and let's see how long this takes to dissolve. Okay, so you can see that this sugar cube, it's falling apart, but it's not falling apart as fast as the other one, where it was just like tumbling and falling apart really quickly. So this one will take a little bit longer, and we'll just wait and see how long it takes. It's been like a minute now, roughly, and there's like majority of it's well broken down. I don't know if you can see very well, but it's mostly broken down. It's just all sitting at the bottom, and the water will slowly dissolve this. We'll just have to wait and see how long it takes. So this is our control group, and it's been nearly 6 minutes, 30 seconds, and it's nearly done. There's just like a couple crystals at the bottom, if you can see right there. In the center, there's a little bit left, but that'll probably take another second, so we'll just wait. But it's pretty much done. It took 6 minutes and 30 seconds right here. So I will write that down, and I will get prepared for our last info. Okay, so now we lastly have our cold water cup here. You can see that there, and I'm gonna put the cold water in now, and we're gonna see how long this takes. So all the cold water is in, and you see the sugar cube that we have here is just beginning to slightly break down. You see that? But it's going to take a really long time. So we'll just wait and see. I'm telling you right now, it's going to take much longer than the rest, because stuff like this generally requires heat. But we're going to show you, this is proof, so you don't have to take my word for it. You can see in real time that this is going to take much longer than everything else. Okay, so I'll see you when this all here is gone. It's in the water. It's in the water. Camera, but it's done now, and it has taken 13 minutes and like 24 seconds. So I'm gonna record that. I'm gonna do some other trials off camera, but they'll probably be all the same, roughly, maybe a couple like second deviation, because you can't get the exact temperature. Like, it's weird, but yeah, they'll all be pretty similar. You'll see like the control group is generally like the most average, the hot ones take the fastest and the cold ones will take the slowest. So that's pretty much it, and you'll see me next when we're reviewing all of our results. So that'll be pretty cool, but until then, adios.
Hello, I'm Nicole and I will be going over stirring. So I understand that most of you know what stirring is, but the reason that stirring is so important is because you want to make sure that your solutes and your solvents will, everything gets dissolved and mixed together correctly or efficiently or, Anyways, so before you start, you need a hypothesis. So the hypothesis is, if I stir constantly 1 cup, then that cup will dissolve faster because agitating the solvent allows the solid to erode at the solvent pieces faster, right? So let's see if this is correct.
Alright, so first we're going to put 1 sugar cube into a cup of water and start the stopwatch. Now it's done dissolving at 7 minutes and 32 seconds. We're going to put another cube in another cup of water and then start the stopwatch and begin stirring at the same time. Now it's done dissolving at 1 minute and 3 seconds. Now let's compare results. Well, it looks like my hypothesis was right, because mixing emulsifies things faster.
Hi, my name is Ahil Mahendra, and today I will be showing you the effects of the surface area to volume ratio on the dissolving rate of sugar. Now, what really is dissolving? When sugar, or in this case the solute, meets the solvent water, certain interactions take place between them. The sugar molecules themselves break up and actually associate and form bonds with the water molecules. This leads to them combining, essentially, and forming a solution, which is the process of dissolving. So, what does the surface area to volume ratio have to do with this? Well, it is my hypothesis that as the surface area to volume ratio increases, the dissolving rate will also increase because there's more space for more reactions to take place with the water. Now, what exactly is the surface area to volume ratio? Well, surface area itself is the amount of area that each face of an object takes up, essentially the outer parts of the object. However, the volume is the amount of space the object takes up as a whole. So in this case, with a block of sugar, it has 6 faces, which would all add up to the surface area. However, as a whole, it forms a very large volume. Now, these 6 faces are very insignificant compared to the entire volume of this cube, which would make it so that the surface area to volume ratio would be very low. However, with the same type of sugar in a very fine powder, the surface area to volume ratio is very high. And this is because the surface area is very large in these tiny sugar molecules, while the volume is very tiny, which would mean that the surface area to volume ratio would be very high. Now, let's see how this really affects the outcome of our experiment and how the surface area to volume ratio affects the dissolving rate. Here are all the materials we will need for this experiment. Firstly, you would obviously need sugar. 1 block of sugar fully, and the same type of block but ground up, preferably in a grinder. That's to ensure that there's the same mass involved in both of them. Along with that, you would need 2 tumblers, each with 1 cup of water in them. Make sure that the water levels are the same and that the temperature in both of them are also similar. Along with that, you'll need a phone or something that can be used as a countdown to see how fast the rate of dissolving will take place. First, we're going to test this block of sugar. This is because this block of sugar has the least surface area to volume ratio, meaning that it is perfect as our control group. So, to start this, have your stopwatch ready, and slowly put in the water into the cup that contains the block of sugar. From here, start the countdown, and as you can see, it is slowly dissolving already. You can see here, there are basically no remnants of the cube of sugar, meaning it is completely dissolved. Now this happened at 8:20, so it took 8 minutes and 20 seconds for a complete dissolving. This is quite a long time, but that's to be expected because, as previously shown, the dissolving rate was quite slow. Now that we're finished with the cube of sugar, we're going to see how the fine sugar fares. Now, this change of surface area with the fine sugar is actually the independent variable because it's the one variable we're changing to gain a greater understanding of how the surface area affects the dissolving rate. And the dependent variable in this case would be how long it takes for a complete dissolving to occur. Now, just like with the cube sugar, you want to very slowly and carefully place this water inside to make sure that it is essentially very similar to the cube sugar. Now, as you can see here already, the fine sugar has immediately started dissolving most of it, and the rest is probably soon to come. So we can be expecting a very short amount of time to pass by. But we'll get to you later. The fine sugar at 2 minutes and 24 seconds has already completely dissolved. Now, it likely could have taken a little less time if we added the sugar to water instead of adding water to sugar. But we had to do that in order to maintain the controls between our experiment and my other teammates. We can now finally make our conclusions. This glass contained the sugar cube and took 8 minutes and 20 seconds to dissolve, and it also had the low surface area to volume ratio. This glass, on the other hand, had a high surface area to volume ratio with the fine sugar and took 2 minutes and 24 seconds to dissolve. Now, this considerable difference between the two must be caused by one main factor, which can be decided as the surface area to volume ratio based on the fact that it is the only independent variable that we change. So, based on that and these results, as the surface area to volume ratio increases, the dissolving rate also increases, and as the surface area to volume rate decreases, the dissolving rate also decreases. But this is not the end of our experiment, even though this complies exactly with our hypothesis. This is because we must do multiple trials, and that is because of confounding variables. Confounding variables are variables that affect your experiment even though they weren't meant to. For example, the fan that I have running in the background could possibly cause the speed of the sugar molecules in one of these glasses to move faster and as such react faster. So, by making multiple trials and getting consistent results, we can rest assured that our results are at least valid and repeatable. From there, to make it into a theory, we would have to do a peer review discussion and discuss our results with fellow scientists, which we will actually be doing in a couple of seconds.
Okay, hi guys, we're back. So as you can see, this is my data table with all the data I collected. The first row accounts for the trials that I did on camera with 7 minutes and 30 seconds for our control group. As you can see in the other trials, it all lined up around the same, around the 7-minute mark. The hot water generally stayed around like 2 minutes, 15 seconds, around there. And the cold water stayed around like the 13-14 minute mark. It was pretty consistent overall. Any errors that could happen could include maybe the water warming up or cooling down, depending on the temperature around it. That's about it, really. Yeah, so what happened with yours, Nicole?
Well, mine was basically around the same thing. Like, the control group stayed the same, just like this third, or like the experimental group. The control had a meeting of about like 7 minutes, and the stirred had a meeting of about like a minute, less than a minute. Some of the errors could have been that maybe I stirred too quickly, like some too quickly or some too slow, or that maybe I didn't realize it, but there was like a slight change in temperature or something like that. All of those things I feel like could have been like a human error, and it could have like affected the results. But overall, I mean, you can see like a visual representation, you know? So what about you, Matthew? What about your
So yeah, I explained my errors. The reason why is Nicole and ours occur this way is that basically heat and kinetic energy on a molecular level are the same, right? So a hotter cup will dissolve things faster, same as a stirred cup will dissolve things faster, because a solute in a solvent with more kinetic energy will dissolve faster because it eats away at the solute faster, right? A solute is something placed in a solvent. So in our case, the water is the solvent and the solute is the sugarcane. So Ahil, what happened with yours?
So my trials were based on surface area around the cube or the fine sugar. And my control group was the full sugar cube, which had a less surface area to volume ratio than the fine sugar, and it took much longer than the fine sugar to dissolve. And the reasoning for this was that as the surface area to volume ratio increased, there was a much more surface per volume. That means there would be more space that can react with the water than if the surface area to volume ratio was smaller. So, for example, with the cube, when it fell in the water, it needed all of its volume to react with the water to fully dissolve, but it could only react on the outer surfaces. With the fine sugar, though, there was a tiny bit of volume, and it was completely surrounded by water on every single side, meaning it could react much faster than the full cube. And my couple of human errors that could have been there was to ensure that I had the same mass of fine sugar and the sugar in the sugar cube. I ground up a sugar cube in like a mixer. And while doing that, there was a tiny bit of sugar that came out, which could have skewed my results just a little. Along with that, my water was a bit cooler than Matthew and Nicole's, which made the control group take a longer time to dissolve.
Okay, so that's our video. Thank you for watching. I hope you enjoyed and I hope you learned something.
Thank you, everybody.
Bye.